Hi everyone, welcome back to Physical Science Online. This is Ms. Vukovic for the AHS Physical Science team on behalf of myself, Ms. Barnes, and Ms. Lackey. This week we are going to talk about radioactive decay and a term called half-life. For this week, we want you to be able to calculate half-life, and we want you to understand the importance of half-life. In order to calculate, you will probably need a calculator, but you'll also be able to look at a graph and read half-life as well from that. All right, so what is half-life? In order to understand what half-life is, we need to understand radioactive decay. Last week, we talked about how radioactive atoms, will undergo radioactive decay. And that's really when their nucleus of the atom breaks down and releases radiation and ultimately turns into a new atom. So we know that atoms that are radioactive are going to undergo decay so that they can become more stable. And the amount of time that it takes for them to decay is called half-life. So half-life is just the amount of time that it takes for a radioactive atom to decay. Scientists have been studying half-life in radioactive atoms for a while, so they already know what the half-life will be of different atoms and different elements. So by studying them and understanding how much time it takes for that atom to decay, they've been able to catalog most of the elements on the periodic table. It's really interesting because based on different element properties, some half-lives are less than a second and some are billions of years. So there are some that last longer, which can be more harmful to us, and some that are really quick and that are not as harmful to us because they don't last as long in our bodies. Okay, so like we've mentioned, a half-life is an amount of time that it takes for a radioactive sample to decay half of its radioactive material. So when we look at a chart like this, number of half-lives is going to be always whole numbers. So 0, 1, 2, 3, 4, 5, 6, 7. 0 represents the start. So 0 represents like when you start, this is how much you have. From 0 to 1 and 1 to 2, those are going to be given an amount of time. So some half-lives, like I mentioned in the slide before, can be less than a second. And so every time less than a second passes, you get a new half-life. It could be a billion years, and every time that billion years passes, you have a half-life passing. So half-lives are just simple numbers to represent a more descriptive amount of time. But what's actually happening during a half-life is that your radioactive material decreases by half. So at time zero, you have 100% of your sample. And for us, we're going to use 100 grams of radioactive sample. After the certain amount of time passes that is specific for our half-life, you have 50% of your sample. And that's what we mean by half-life. Your sample is going to decrease by half. So you had 100 grams, now you had 50. And you can figure that out by dividing by 2. Oops, So you can divide by 2. Then again, for your next half-life, you know that a certain amount of time passed and you got rid of another half of your sample. And so you were at 50, you divide by 2 again, and you get 25. So what you guys want to be able to do is look at this part and calculate the amount of remaining radioactive material based on this percentage, and also recognize that every time you divide, you're getting a new half-life which would be representative of a certain time. Something to pause and think about is some vocabulary. A lot of times we talk about our time zero as the start. And when we talk about the start, we're looking at radioactive material and radioactive nuclei. And we always call radioactive nuclei parent nuclei or parent nucleus. And that's because it's what we're starting with. Once that nucleus undergoes decay and becomes more stable, which is the whole point of radioactive decay, we end up with something that we call a daughter nucleus. And that's just our new nucleus or a new atom. So as each half-life goes by, you're going to get more daughter nuclei and less parent nuclei, because we know that the radioactive, which is unstable, is turning into stable. And that's the goal. All right, so all that information, we're going to try to do an example together. This example says an isotope of cesium has a half-life of 30 years, which means every 30 years, half of that sample is going to decay and become stable. This question says if 10 grams of cesium-137 decays over the course of 90 years, how much would remain? So what I would do is make a table. And I would start with your time. So we know that time always starts at 0. Then we know that it lasts 90 years. So we know that our max wants to be 90. In order to figure out the time in between, you want to look at your half-life. So we know that half-lives are measured by 30 years. So I'm going to go 0, 30. 30 plus 30 gives us 60. 60 plus 30 gives us 90. That's the amount of time that passed. For half-life, so I'm just going to put an HL, we want to start with 0 because that's the start. At the start, we have 0 half-lives. After 30 years, we have 1 half-life that passed. After 60 years, we have 2 half-lives that passed. And after 90 years, we have 3 half-lives that passed. So we have our time. Then we want to know our sample amount. So the amount. And I'm just going to put number because that reminds me of how much. There we go. At the beginning, we have 10 grams. We know that we are going to have 100% at 0, and then we divide by 2, so we would have 50% at half-life 1, we would have 25% at half-life 2, and we would have 12.5% at half-life 3, because each time we divide by 2. If that doesn't make sense, like if this part doesn't make sense to you, you can always just go back to basics and just divide this number by 2. So for half-life 1, we have half of 10 left, which is 5. For half-life 2, we have half of 5 left, which is 2.5. And for half-life 3, we have half of 2.5 left, which is 1.25. So our answer is after 90 years, you are only going to have 1.25 grams of cesium-137 left. Another cool way you can look at half-lives is through a graph. You can graph the number of parent atoms that are radioactive, which would be in the blue. And those are all the ones that are radioactive, and you'll see that over time it exponentially decreases and you end up having less of your sample left. And as your radioactive ones decrease and turn into new nuclei, stable nuclei, you'll see that the number of daughter atoms that are stable increases. So the reason we talk about this is because Radioactive material can be pretty present. You can have radioactive waste, and it's important to know the half-life of radioactive atoms so we know when it will decay. If we ever have a spill, it's helpful to protect people from radiation if we know the half-life. We can also use half-life to understand the released radiation, and we can use it to do radioactive dating. So half-life is important for a lot of different information. So one of the cooler things, like I mentioned, is radioactive dating. We can use radioactive material in order to figure out the date or age of different rock samples or samples that we found from Earth's material. So scientists most often are going to use carbon-14, and you can use that to understand the age of an organism or rock sample. But it has to be within the last 50,000 years, or else it cannot use carbon-14. So that's radioactive dating. This was half-life. And half-life, again, is just this idea that there's a given amount of time that it takes for any radioactive sample to decay 50% of its material. All right, so that's radioactive decay and half-life. I hope that you guys are able to work through some of the calculations. I linked some videos to the PowerPoint, so if you want to read or watch those, it's gonna be very helpful. If you have any questions, as always, reach out with email. I know that this week is a little more math-based, so good luck, and I hope you guys are doing well.